Hi dears, today we are going to see MCQ series 2 in Algebra. The first one is if P is prime and P divides order of G, then out of this 4, option A is right. A power P belongs to G. Second one, if A belongs to G is of order N, that is order of A is equal to N, and P is prime to N. That means P comma N is equal to 1, relatively prime. Then the order of A power P is equal to, the answer is N. Order of A is N and Pn is equal to 1. Then order of A power P is also N. Now the third one, if in a group G, A belongs to G, the order of A is N and the order of AP is M, then out of this 4, the option A is right. So here order of A is equal to N and order of A power P is equal to M. We can see by example. Here I power 1 is equal to I, and I square, which is equal to minus 1, I cube is equal to minus I, and I power 4 is equal to 1. Right? Now if I am taking I square, the element I square, so that I square, so the first element I took, A is equal to I. So there the order I got as 4, order of 4 which is equal to 1. So that I can say that order of I is equal to 4. Now I am taking the next element I square. So I square is equal to minus 1. I square the whole square which is equal to I power 4 which is equal to 1. So here the order of element, that is A power P, I am taking as I square, and that order is, here you can see the order which is 2. So this is equal to N and this is equal to M. So from this you can say M less than or equal to N. So this condition is satisfied. If I take the element I and whose order which gives 4, that is whose order of I which gives the identity element, that is 4. Similarly, I took the another one element I square and whose order, here I square the whole power 2 which gives the identity element whose order is 2. So 2 less than or equal to 4. So option A is correct. Now the fourth one, if G is a group and A belongs to G such that A square is equal to A, then A is equal to the identity element. So this is the condition for projection. The condition for projection, A square equal to A, and this A is called the identity element. Then we can see the fifth question. The generators of the group G equal to A square, A cube, A power 4, 5, A power 6 is equal to the identity element. So what are the generators? So we have a result that an element A power P of the finite cyclic group of order N is called the generator. That is AP is called the generator if and only if it satisfies 0 less than P less than N, and also it is, that is N comma P or relatively prime. So such a way we have to find this one. So I am taking the element here A. So A power 1 A, then A power the whole square, that is equal to A square, right, A the whole cube, A cube. So what we have to check here is the order. Here it is 1, right, A power 1. So 1 less than 2, that is P less than N. Also it is relatively prime. 1 comma 2 is equal to 1, satisfied. Similarly A power 1, so 1 less than 3 and 1 comma 3 is equal to 1. Similarly A power 1 the whole power 4, 1 less than 4, so 1 comma 4 is also 1. Again you can see the whole power 5, 1 comma 5 is relatively prime, and A power 1 the whole power 6, that is 1 comma 6 which is equal to 1. all these conditions satisfied 1 less than, that is P less than N. That is the important condition. Together with it is relatively prime, right? So that these all conditions satisfied, hence we can say that this is the generator. Now we can see the next elements. I'm taking the next element here, a square. I couldn't able to take this whole power 1, because we have the condition p less than n. Here it is 2 greater than n. So I couldn't able to take power 1. So start with a square, the second element, the whole square. This is also not possible because p less than n. So start with 3. So 2 less than 3 and also 2 comma 3 is relatively prime. So a square the whole power 4. So 2 less than 4, but it is not relatively prime. Common factor 2 is there. So one of the condition is doesn't hold. So a square is not the generator. Similarly, you have to take the other elements. A cube. So a cube you start with the 4 because 3 couldn't be possible. The condition is p less than n, not less than or equal to. So start with the 3 less than 4 and 3 comma 4 is relatively prime, and a cube the whole power 5, which is 3 comma 5 is equal to 1, that is relatively prime. A cube the whole power 6, 3 less than 6, but 3 comma 6 is not relatively prime. So a cube is not the generator. Such a way you have to check for the remaining elements. Now I am moving to a power 5. So a power 5 the whole power 6, because we won't move to 4 or some other value because p less than n. So here it is satisfied 5 less than 6 and also it is relatively prime. So I can say that a power 5 is generator. So here is the correct option is A and a power 5. You can check with the remaining generators. So these two generators we check, as such you have to check the remaining. So here is A and a power 5 are the generators. And the sixth one, every group of prime order is cyclic. Seventh one, if H is the subgroup of finite group G and order of H is the subgroup, order of H and G are respectively M and N. So this is the order of H and this is order of G. Then order of M divides order of N. So this gives from Lagrange's theorem. So Lagrange's theorem states that order of the subgroup divides order of G. So here order of H is M, M divides order of N. Now the eighth one, all the cyclic groups are abelian and order of the cyclic group is same as the order of its generator. So which of the options are right? So all the cyclic groups are abelian, that's right, and order of cyclic group is same as the order of generator. So A and B are true. So you can see here all the cyclic groups are abelian is the result, and order of the cyclic group is same as the order of the generator. You can see here. So I am taking the group here 1 minus 1 I minus I. It is a cyclic group of order 4. Now we need to check that order of a generator is equal to the order of the cyclic group. So for that I power 1 is I square, because we know that in this cyclic group the generators are I and minus I alone. Because if I take I power 1, I am getting I square which is minus 1, I power cube which is minus 1, I power 4 is 1. So it satisfies, it is whose power giving all these elements. So this is a generator. Similarly, minus I the whole power 1 which gives minus I the whole square which gives the next number, minus I the whole cube and minus I the whole power 4 give all these elements. Hence we can say this is the generator. Now here you can see that this generator I am taking I power 4 which I am giving the identity element. So for checking this, first you have to find the identity element, that is under multiplication. So this is the identity element, this one, 1. So I power 4 gives 1. So whose order is what? 4. So order of this generator is equal to 4, which gives identity element, and the order of the cyclic group is also 4. Order of cyclic group is also 4. So that we can say that order of the generator is equal to the order of the cyclic group. Here I and minus I are the generator. If I take minus I the whole power 4, it also gives identity element 1. So order of the generator is equal to order of the cyclic group. So both options are right. Now we can move to the 9th question. In the additive group of integers, the order of every element, that is non-zero element is. So we have that additive group of integers. If we add all the elements, should give the additive identity element, that is Na is equal to 0, A plus A plus A plus etc., which gives the identity element. But here you couldn't able to see any non-zero element which gives the identity element. We can see that 1 plus 1 plus 1, that shouldn't be give 0, or minus 1 minus 1 minus 1 won't give that as 0. So it is impossible. So we can write that it is infinity. Similarly, this question, in the additive group of integers, the order of the inverse is also infinity. Now the 10th one, a ring R is an integral domain if R is a commutative ring without zero divisors is the right one. If it is an integral domain, then it is a commutative ring without zero divisors. The next question, a skew field have non-zero divisors. It's a result. Skew field have non-zero divisors. And the 12th one, which of the following statement is false? A skew field have zero divisors, and integral domain, an integral domain have zero divisors. So these two also false. So just before we see a skew field have no zero divisors. So this is wrong, and also integral domain is also have non-zero divisors, because the 10th problem you see that integral domain is a commutative ring without zero divisors. So from this you can say that skew field have no zero divisors. Also integral domain also have does not possess zero divisors. So these two options is true for that is correct for this question. 13th one, a field have no proper subfield is a prime field. 14, every finite integral domain is of finite characteristics. That is, the condition is there, Ma equal to 0, when A not equal to 0 gives M equal to 0. This is the condition for finite characteristics. So if it is a finite integral domain, then it is a finite characteristic. Then every non-zero nilpotent element of the ring is non-zero nilpotent element. So I am taking the element as A. So A power n, the nilpotent element, which is equal to E, which is equal to 1. That is unity. So every non-zero nilpotent element is unity is the right answer. Thank you.